In this video, we'll be going over L'Hopital's rule. So to start, think back to when we were working on limits. So recall when we had something like this, the limit as x goes to 0 of 1 minus cosine of x divided by x. If we used direct substitution here, we would end up with 1 minus cosine of 0 is 1, so 1 minus 1 in the numerator is 0, and then we'd end up with 0 in the denominator. We called this an indeterminate form. Similarly, if we took the limit of, or the limit as x goes to infinity of something like this, 3x plus 5 over 2x plus 1, by direct substitution here, we'd end up with infinity over infinity. So in both of these cases, we're kind of stuck. So with the tools we had when we were first working on limits, for both of these limits we would have been stuck. However, there were other things that we could do. But L'Hopital's rule is a strategy that we can use when we have this type of indeterminate form. So indeterminate form, and specifically 0 over 0 and infinity over infinity. So here is the definition of L'Hopital's rule. It says if the limit as x goes to a for a function f of x is equal to 0, and the limit as x goes to a for a different function g of x equals 0. So if both limits equal 0, or if both limits equal, I have a typo here, this should say plus or minus infinity. So if both limits equal 0 or both limits equal infinity, so what we can do is if we divide, if we have the limit of this quotient, what we do is we can take the derivative of the numerator and the denominator to evaluate. So in other words, if we have some limit, that is and we're taking the limit of a quotient, and if we end up with something like 0 over 0 or infinity over infinity, so either of those indeterminate forms, and that's plus or minus, then what we can do is we take the derivative of the numerator and the derivative of the denominator, and then we can try to evaluate the limit. And so this is going to work when x is equal to a, or as x approaches a, or as x approaches plus or minus infinity, or a from the right-hand side or the left-hand side. So let's look at a few of the initial examples where we can apply L'Hopital's rule. All right, so this first limit that we're going to evaluate is the limit as x goes to 1 of x cubed plus x squared minus 2x divided by x minus 1. Now what we were doing when we were first working on limits is we would first try direct substitution, and we'd have 1 plus 1 minus 2 divided by 1 minus 1, and we'd end up with 0 over 0. And this is an indeterminate form. I'll just write I dot f. And what we might have tried to do previously was to see, well, is there a common factor between the numerator and the denominator? In other words, can we factor the numerator so that we have a factor of x minus 1 in the numerator, and then we could cancel that out, and then again try direct substitution. A different method is to use L'Hopital's rule. If we end up with something in this indeterminate form, 0 over 0, what we're going to do is we're going to take the derivative of the numerator and the denominator. So the derivative of the numerator is going to be 3x squared plus 2x minus 2. The derivative of the denominator is just 1. So now doing direct substitution, we end up with 3 plus 2 minus 2 divided by 1, and that's just going to be 3. So the limit here is going to be equal to 3. Okay, next example says to evaluate the limit as x goes to 0 of e to the x minus 1 over x squared. And by direct substitution here, e to the 0 power is 1, minus 0 minus 1, divided by 0 squared, which is just 0. So we end up with 0 over 0, which is, again, an indeterminate form. So we're going to apply L'Hopital's rule here. So apply, I'll just write it like this. Apply L'Hopital's rule. So we're going to say the limit as x goes to 0. Now we're going to take the derivative of the numerator separately from the derivative of the denominator. I should say a common mistake students will make is they'll apply the derivative using the quotient rule, but that's not what we want to do. We want to apply the derivative of the numerator, the function in the numerator, separately from the function in the denominator. So term by term in the numerator, the derivative of e to the x is just e to the x minus 1, and then in the denominator we get 2 over x. And so let's see what happens when we do direct substitution. E to the 0 power is going to be 1 minus 1 divided by 2 times 0. So again, it looks like we end up with an indeterminate form. Now, that seems like a problem, but what we're going to do is we're going to apply L'Hopital's rule again. To see if we can, in a sense, reduce this down to something where we have a limit that is not an indeterminate form. So the derivative of e to the x minus 1 is just e to the x, divided by the derivative of 2x is 2. Now e to the 0 power is 1, and then the denominator just stays at 2. So what we end up with here is 1/2 as our limit. All right, our next example, we want to evaluate this limit. So as x goes to 0 from the right of the natural log of x divided by cotangent of x. So as x, I'm going to look at a graph here. So as we're approaching 0 from the right-hand side, ln of x, well, that graph looks something like this. Something like that. So as we're getting close to 0, the graph goes to negative infinity. So when we use direct substitution here, this is going to be negative infinity in the numerator. And then the graph of cotangent, I'll do that in blue here. The graph of cotangent is a decreasing graph. And it does something like this. And it keeps repeating. So when we're getting close to 0 from the right-hand side, cotangent is going to positive infinity here. Okay, so what we see is that this is an indeterminate form. So what we're going to do is we're going to take the derivative, we're going to apply L'Hopital's rule, and that just means take the derivative of the numerator and the denominator. So the derivative of ln of x is 1 over the argument, so 1 over x, divided by the derivative of cotangent of x is cosecant squared of x. Now, before I use direct substitution here, I'm going to simplify this limit. So we can rewrite cosecant squared of x as 1 over sine squared of x. So in the numerator, when I simplify this limit, I'm going to have 1 over x divided by 1 over sine squared of x. So I can rewrite this as sine squared of x divided by x here. Okay, so I'm going to apply L'Hopital's rule, which just means, I'm going to use a direct substitution here. So the limit as x goes to 0 from the right for sine squared of x. Well, sine squared of x, I'm just going to rewrite this as sine of x getting squared. So sine of 0 is 0. And then 0 squared is still 0. And then using direct substitution in the denominator, I also get 0. So again, I have another indeterminate form. So I'm going to apply L'Hopital's rule again to this limit. The limit as x goes to 0 from the right of sine of x getting squared over x. So taking the derivative of this, of the numerator and the denominator, so what we end up with is the limit as x goes to 0. So the derivative of sine of x squared, so that's going to be 2 sine of x raised to the first times the derivative of sine of x, which is cosine of x. And then in the denominator, the derivative of x is 1. So now using direct substitution, I'm going to plug in a 0 here and a 0 here. So sine of 0 is 0, so that whole numerator is going to be 0. The denominator is 1. 0 over 1 is not an indeterminate form. It's just equal to 0. So this original limit, what we found, is that this limit is equal to 0. So what we've seen here in these last couple examples is that we may need to apply L'Hopital's rule more than once. And we just need to remember that there are a few different indeterminate forms that we could come across. So far we've seen infinity, plus or minus infinity divided by plus or minus infinity, and then also 0 divided by 0. In either case, we can apply L'Hopital's rule, and we may need to do that a couple times to come up with a solution. All right, our next example, we want to evaluate the limit as x goes to infinity of ln of x over 5x. And by direct substitution, we can see that this gives us infinity over infinity. So let's apply L'Hopital's rule. I don't know why I wrote a lowercase l there. Let's be consistent. So we end up with the limit as x goes to infinity. So the derivative of ln of x is 1 over x. The derivative of 5x is just 5. So when we use direct substitution, 1 over infinity here, that's going to approach 0. 5 remains the same in the denominator, so that is equal to 0 here. And I think that's all I want to do in this video. Actually, let's do one last example. So evaluate this limit. So as x goes to 0 of sine of x minus x divided by cosine, not cosine, divided by x squared. All right, so by direct substitution here, sine of 0 is 0, minus 0 is 0, divided by 0, so that's indeterminate form. So we're going to apply L'Hopital's rule to the original limit. So as x goes to 0, the derivative of sine of x is cosine of x, minus the derivative of x is 1, divided by 2x. Okay, so by direct substitution, cosine of 0 is 1, minus 1, and then in the denominator we get 2 times 0 is 0, so this is also 0 over 0. We have another indeterminate form, so we're going to apply L'Hopital's rule again. So applying L'Hopital's rule to this quotient, so the limit as x goes to 0, the derivative of cosine of x is negative sine of x divided by 2, and we've seen sine of 0 is 0, times a negative 1 is still 0, divided by 2, so we end up with 0 here. Okay, so we've seen a bunch of examples on how to apply L'Hopital's rule. In the next video, we're going to see a couple of different types of indeterminate forms and how we apply L'Hopital's rule to those indeterminate forms.